Assalamualaikum and hi to everyone. Thank you for watching this video. So in the previous video, we already learned about a part of chapter 7 regarding the deadlock. So in this video, we continue on the chapter 7 regarding the deadlock, and we look for the method handling. So the previous part, we already learned about the system model, the deadlock characteristic, what are the criteria of the deadlock, the resource allocation graph, how to draw the resource allocation graph, and the symbols for the P, for the resources, for the instances, and so on. And then you also being introduced and explained regarding the safe state and the unsafe state. So in this video, we continue on the methods for handling the deadlock. Here we try to look at the deadlock prevention, deadlock avoidance, and then later we continue on to the deadlock detection and recovery from the deadlock. So look at the first part, deadlock prevention. So prevention means we try to restrain, or we try to ensure that there is no possibility that the deadlock can occur in the system. So the restraint way request can be made by mutual exclusions. So that require for shareable resources must hold for the non-shareable resources. Okay, this one is the mutual exclusion, and then we can have the hold and wait. Okay, we must guarantee that whenever a process requests a resources that the system has, it does not hold any other resources. So hold and wait. So require process to request and be allocated all its resources before it's begin to execute, or allow the process to request resources only when the process has none allocated. So this one is for hold and wait and low resource utilization, but it might occur the starvation issue. Okay, for no preemption, if a process that is holding some resources, let's say we have P1 hold the resource 1, so request another resource that cannot be immediately allocated to it, then all resources currently being held are released. So they need to wait for release the resources that it held. So preempted resources are added to the list of the resources for which process is waiting. So this is how the allocation of the resources to the process. Okay, and process will restart it only when it can regain its all resources as well as the new one that it is requesting. Okay, you need to imagine that we have a process can hold the resource or use the resource, and at the same time the same process can make a request. And then circular wait here impose a total ordering of all resource time, and then require that each process requests resources in an increasing order of enumeration. So we have no preemption, circular wait, mutual exclusion, and hold and wait. Okay, this is the way we can restrain the request, deadlock prevention. So for the deadlock prevention, these are the procedure. Okay, we have do work 1, and we use the pthread mutex locks. So these are the codes that we can apply for the deadlock prevention. So the deadlock prevention with lock, the locking function here is used to ensure that each process can be done and that another process can be done. So we need to lock that process. Okay, for example, here we have two process, translation 1 and translation 2. So these two process execute concurrently or simultaneously. So we need to use the lock function to lock that process. Okay, that's why it shows transaction account from and account to, account from account A to the account B. So this is the amount of money. So we use the mutate logs. So get log from and get log to. So we use log function to log the process. So one process is withdraw, another process is a deposit. So after withdraw and deposit, then it will release the log. Okay, so these are the procedure or the code for the deadlock prevention with the log. We use the log function in order to prevent the deadlock. Second part is about the deadlock avoidance. Once we try to prevent, another one we try to avoid. So require the system has additional a priori information. Yep, a priori information. So using the deadlock avoidance, it's required to have additional priori information available. So simplest and most useful model requires that each process declare the maximum number of resources of each type that it may need. So process should declare the maximum number of resources that the process need. The deadlock avoider algorithm dynamically examines the resource allocation state to ensure that they can never be circular weight condition. So using the avoidance algorithm, the deadlock avoider algorithm, this algorithm try to examine the resource allocation to ensure that the circular weight condition never occurred in the system, because we want to avoid on the deadlock. Resource allocation state is defined by the number of available and allocated resources and the maximum demand of the processes. So here we have the resource allocation state, the allocation for process, and then we have the available and the allocated resources with the maximum demand of the processes that we have in the system. Okay, you can look at the avoid algorithm. Single instance of resource type use a resource allocation graph. And then multiple instances of resource type use the banker's algorithm. So if the resource only have a single instance, then we can use the resource allocation graph. If we have multiple instances in our resource type, so we can use the banker algorithm. So resource allocation graph scheme, we have the claim age, P to R, process to resource. So this claim age, this one, indicated that the process P may request resource from R. P request resource from R. So this claim age is represented in a dash line. So example of dash line, okay, this one, dash line. So claim age convert to request age when a process requests a resource. So the claim age will be converted to the request age. Request age converted to the an assignment age when the resource is allocated to the process. So when you make a request and request is allocated to the process, it will convert to the assignment age, a straight line. And when a resource is released by a process, assignment age reconvert to a claim age. Okay, assignment age, this one is the claim age. So resource must be claimed a priori in the system. Resources must be claimed a priori in the system, because in this part, in this avoid algorithm, we need to have a additional priori information. Okay, so look at this graph. Okay, this is a resource allocation graph for deadlock avoidance. So we have the claim age here. Okay, we have resource 1, we have resource 2. Okay, in this case, we assume that we only have a single instance. Okay, we only have a single instance, so we have resource 1 and resource 2. Okay, resource 1 is held by the process 1. Resource process 2 use the resource 1. Then this part is whole, this one is a request the resource 1. Process 2 request resource 1. Resource 1 is held by the process 1. So this is the claim age. So P1 try to make a request to resource 2, and the same thing P2 also make a request to the resource 2. Okay, in this case, okay, this is a situation. So in this case, okay, let's say P2 request from the resource R. P2 is here, request from the resource 2. So based on this one, P2 request from the resource 2. So let's say R2 at this time, okay, you look at this graph. At this time, R2 is not belong to any process. R2 is currently at the free stage, means that there is no other process that use the R2. Okay, we cannot allocate that R2 to the P2 in this case. Okay, in this case, even the R2 is free, no one use it, but we cannot, in order to avoid the deadlock, we cannot allow P2 to use the R2 even the R2 is not used by another process. Okay, why? Because if we allow that occur, then a cycle might be occur in this graph illustration, and it will indicate that the system is an unsafe state. Okay, let's see here, if P1, okay, P1 request R1, okay, P1 request R1 and P2 request P1 request R2. Okay, let's say P1 request R2 and then P2 request R1, then the lock may occur if we allow the P2 at the first part to use the R2, and so the deadlock may occur like this one. Okay, unsafe state resource allocation graph may occur. So this is a circular, or a cycle. So we want to avoid the cycle happen in our system, so we cannot allocate R2 to the P2. So suppose that P1 requires PI request to the RJ. The request can be granted only if converting the request age to an assignment age does not result in the formation of a cycle in the resource allocation graph. So we want to avoid this kind of allocation graph happen. So we want to avoid the cycle in our graph. Okay, the next part is the banker algorithm. This one is the allocation graph. This one is the banker's algorithm. So allocation graph for the single instance. Okay, if the resource have a single instance, so we can use the graph allocation. If there are multiple instances, we need to use the banker's algorithm. So each process must have a priori claim maximum use. So process must have the prior information about the maximum use. When a process requires resource, it may have to wait. And then when a process get all its resources, it must return them in a finite amount of time. So after they use, they need to return it back. So this is the structure of the banker's algorithm. Okay. N is referred to the number of processes and M is referred to the numbers of resources type. So we have 4 situations: available, maximum, allocation, and needs. Okay, available refer to the resources. Okay, refer to the instances of our resources that available. Maximum is refer to the most numbers or the most numbers of instances of the resources that can be requested. Okay, and then we have term allocation. Okay, allocation is the resources that we allocate or the instances that we allocate to the processes. And then we have the needs. The needs is how to calculate is based on the maximum here, maximum minus the allocation. So it's referred to the needs of the instances resources in order to complete the task. So we have the safety algorithm here. Okay, that work and finish be a vector length m and n respectively. So under the safety algorithm, we have work available and finish. So you can go further, but this not cover in the topic. You focus on the banker algorithm and the graph allocation. But we can go through. Okay, here the first part, let the work and finish be vectors of the length m and m. And then find I such as both. Okay, finish equal to false. Needs must equal or less than the work. And if no such I exists, we can go to step number 4. This is the step. Okay, and then work equal to work plus allocation. And finish true, go to step number 2. And then it will loop again until it finish. So if finish I equal to true, so for I, then the system in the safe state. So this safety algorithm to ensure that they are in the safe state. Okay. For a resource request algorithm, okay, request vector for process I. So if request j equal to k, then process pi wants k instances of the resources. Okay. If request equal or lesser than the needs request from the process is equal or lesser than the needs, so we can go to step number 2. Otherwise, we can raise an error condition since the process has exceeded the maximum claim. Okay, this is rule number 1. So if request less or equal to the available, go to step number 3. Otherwise, P must wait since the resources are not available. So if the request numbers is less or equal to available numbers that have, means available is refer to the resources, then we can go to step number 3. Otherwise, we need to wait. Okay, number 3, pretend to allocate requested resources to P by modifying the state as follow. This one based on step number 2. So available equal to available minus the request, allocation equal to allocation plus the request, and needs equal to needs minus the request. So if safe, then the resources are allocated to the process. If unsafe, then P must wait and the all resource allocation state is restored. So these are the steps. So let's look at the banker algorithm. Okay, in this example, we have 5 processes, P0 until P4, P0, P1, P2, P3, P4. So total we have 5 processes. And then we have 3 resources Okay, we have 3 resources. So we have resource A, B, and C. So for A resource, we have 10 instances. For B, we have 5 instances. And for C, we have 7 instances. So at the time 0, we need to identify the allocation, the maximum, and the available. And another part, we need to know the needs. Okay, let's say at time 0, we have 0. For P0, we have 0. For A, resource A, 1 for resource B, and 0 for resource C. This one is the allocation for process 0. So the maximum for process 0, it can go 7, 5, and 3. Okay, allocation is 0. So we can have 3, 5, and 3. This one is the maximum. And available, we have 3, 3, and 2. So 3 for A, 3 for B, and 2 for C. For process 1, we have 2 for A, 0 for B, 0 for C. This one for allocation. For the maximum number, 3 for A, 2 for B, 2 for C. And then for process number 2, we have 3 for A, 0 for B, 2 for C. And the maximum part, 9 for A, 0 for B, and 2 for C. For process number 3, we have 2 for A, 1 for B, and 1 for C. For the maximum part, 2 for A, 2 for B, and 2 for C. And then for process number 4, allocation 0 for A, 0 for B, and 2 for C. And the maximum numbers, 4 for A, 3 for B, and 3 for C. So based on this part, we can calculate the needs. How to calculate the needs? The maximum minus the allocation. Okay, the needs contents of the matrix defined by maximum minus the allocation. So for P0, okay, for P0, maximum minus 0, 1, 0 minus allocation, so equal to 7 for 3. So we got 7 for 3 here. For process number 1, 3 to 2 minus 2, 0, 0. So we'll get 1 to 2. Okay, 1 to 2 here. And then we have 902 minus 302. Then we will get 600. Okay, 600. And then we have 222 minus 211. So we'll get 011. Okay, 011 here. And here we have 433 minus 002. So we'll get 431. Okay, 431. So these are the needs for the example. Process 0, process 1, process 2, process 3, and process 4. So based on this part, we can say that this is in the safe state since the sequence is equal to P1 and then followed by P3, P4, P2, and for P0. So it will satisfy the safety criteria. How to get the sequence of P1, P2, P1, P3, P4, P2, and P0? Later on, we will discuss on the example. Okay. So here, another example, check request available. So 102, either it's equal or less than 332. So this one is true. So we can identify the allocation, the needs, and the available. So based on this one, the executing safety algorithm shows that the sequence P1, P3, P4, P0, P2. And it asks, can request 330 by process 4 be granted? Okay, this one, they want to request 330 can be granted. and then can request for 0 to 0 by process 0 can be granted. So it's based on the needs and available here. So later on we will look for the example. So that's all what we have learned here is about the method of handling deadlock. We cover on the deadlock prevention and the deadlock avoidance. So later on we will look for the example and continue on the methods. So thank you and assalamu alaikum.